Hi everyone, welcome to the final video for Kines 7103 where we're going to be talking about systematic violations of our error assumptions. So in the other videos in this module, we've been talking about how to deal with sort of idiosyncratic violations in error when we're looking at our regression diagnostics to look at, outliers, points with leverage, or influential data points via Cook's distance. In this final video, though, we want to kind of consider larger scale violations when we're talking about or how our residuals as a whole violate our assumptions. So the first assumption that we want to talk about is normality, and the normality assumption means that we assume that our residuals follow a normal distribution. And as long as they follow a normal distribution, right, or as long as they approximate a normal distribution, the p-values that we get when we calculate our inferential tests will be accurate. And the more we deviate from that assumption of normality, the less and less accurate our p-values become. So one way in which this assumption can be checked is with what's known as the quantal-quantal normal plot that we, for instance, get out of R, where we're looking at the standardized residuals as a function of the theoretical quantiles. So these are the standardized residuals, right, which can be roughly interpreted as z-scores. So if you have negative values, right, you're below the mean. If you have positive values, you're above the mean. And then these are in units of the standard deviation. The theoretical quantiles then correspond to, under a perfectly normal distribution, what should those quantiles be? So the diagonal line that we draw across this is the one-to-one relationship between the standardized residuals and the theoretical quantiles. So if you're on this line, this means that you perfectly line up with what the empirical probability was and what the theoretical probability should be. So the more we deviate from this line, which we do in sort of the upper part over here and the lower part down here, that means we're moving away from normality. And our assumption of normality is, pretty lightly violated in this case. These aren't perfectly normal residuals. So we can actually check this also more quantitatively with goodness of fit tests like the Shapiro-Wilk test or the Kolmogorov-Smirnov test. And those aren't things we actually cover in this course, but you might go on to do them in your own work or see them covered in other classes. But they will actually tell you whether or not the normality is violated to a statistically significant degree. There are some limitations to that sort of assessment, and the main thing I would encourage you to do is remember that violation is continuous, not categorical. So even if your Shapiro-Wilk test or your KS test was not statistically significant, you could still be violating normality to some degree. And the more and more you violate normality, the less and less accurate your p-values actually are. And I think that's really important, especially if we consider how we want to interpret a fairly marginal p-value, like a p of 0.04. Right? If we have a p-value of 0.04, but we have minor violations to normality, well, do we really, that could easily be a p-value of 0.05. So we want to consider that there's a little bit of error in the estimation of our p-values. And we can try to control it by checking our residuals, but we always want to be cognizant that there's still a little bit of error in the estimation of those p-values. They're unbiased, right? But they aren't necessarily going to be perfect. And the more we deviate from the assumptions of our model, the less and less accurate those p-values are going to be. So what happens if we violate this normality assumption? So shown here, we have a very clear violation of the normality assumption, where we have a lot of data points that fall pretty much directly on the line. They line up nicely with a perfectly normal distribution, but then we have some data points that are massively off the line. So this would represent a pretty substantial violation of normality. And in this situation, we aren't actually going to get any bias or inefficiency in our estimation. So the values that we estimate for those betas will be the values that produce the smallest sum of squared errors in our sample. So we'll get the same sort of slopes that we would normally get. But where it is going to cause a problem is in the calculation of the standard error or the mean squared error, and therefore the calculation of our p-values when we go on to look at the probability of obtaining a particular f observed or the probability of obtaining a particular t observed. And the more these residuals depart from normality, the less reliable our p-values are going to be. The second major assumption that we need to deal with is homoscedasticity. And the assumption of homoscedasticity is that our residuals have an equal variance across all levels of the fitted values. So for instance, here's some data from where we had a two-group comparison of younger adults and older adults. So we're looking at their standardized residuals on the y-axis. All of the older adults had one predicted value, so that's why all these data points line up down here. All of the younger adults had one predicted value, right? Because we're looking at these things as two different levels of a categorical factor. So they have the same predicted value up here. And what you can see is that although, there is a bit more variability in the older adults than in the younger adults, it is not statistically greater. These things aren't too different, right? We're all around about 1.5 in terms of the squared value of the absolute standardized residual. And if we fit a regression slope to this relationship, that regression slope looks pretty flat. So it looks like the variance is really pretty comparable between our older adult group and our younger adult group here. And in this case, we would have fairly homoscedastic data because the variance across all levels of our outcome measure is the same. So this assumption can be checked by something like the scale location plot like we've just drawn, or by regressing the standardized/studentized residuals onto the fitted values and calculating a p-value to see is the slope of that line statistically significant. Again, though, we run into issues that, although it's kind of nice to have that cutoff of is it statistically significant or not, the problem is that violations are continuous, not categorical. So even though it's not a statistically significant violation of homoscedasticity, the more we deviate from perfectly even variability, the greater and greater our violation becomes. So what happens if we violate this assumption? Well, in ordinary least squares regression, when we do calculations, for instance, of the mean squared error or standard errors, we are assuming that we have a constant variance across all levels. So if we have heterogeneous residuals, right, where we have greater variability for some values than we have for other values, we're again going to have less reliable p-values. It's not going to create any bias in our estimate, but when we go to make that statistical inference and try to make some sort of hypothesis test, if we violate this assumption and we have heteroscedastic data, right, which is to say we have a non-constant error variance, we're going to be creating some error in the p-values that we calculate. So to illustrate this, I want to walk through three different situations. One in which we have relatively well-behaved residuals, one in which we have clear violations in our residuals, and one where it's sort of a middle ground and it's a slightly more difficult problem, where we see a little bit of a violation, but how do we handle it? So first, let's consider the case of well-behaved residuals. So this is a hypothetical data set where we're looking at some scores on a cognitive test as a function of which group you're in. Were you in the younger adult group or were you in the older adult group? And as you can see here, the older adults generally tended to score worse on this cognitive assessment than the younger adults. We can actually plot then the residuals around this regression line, right? So we can say, okay, if we estimate one value for what the mean was in the older adult group and what the mean was in the younger adult group, here's how our residuals are distributed. And you can see that that's actually slightly different than if we just look at the distribution of the y values themselves. So if we just look at the distribution of those y values, right, this histogram has a different shape with sort of a thicker part in the middle than this histogram where we're looking at the residuals. In either case, we do have this outlier down here where we have a value pulling down or widening out the residuals because we have this single very low score in the y values over here. So our assumptions always apply to the residuals and not to the data themselves, right? But I just wanted to reinforce that these two things are different because it's not the distribution of the data that matters, it's the distribution of the residuals that matter, because our assumptions are always going to apply to the residuals and not to the data. So we can check these assumptions using a number of plots, and in R, what we can usually do is just create a linear model, and then we can run the function plot, and then give the plot function the name of the model that we just created, and then you'll have to hit the enter key in order to channel through these different plots, but you can see 4 or 5 diagnostic plots in a row that all tell us something about the assumptions of our model. And you can get these out of other statistical programs. The actual code to do so might be a little bit different, but in R, this is how that looks, right? So we run plot and then the name of our model. Let's say this was our model here. We're predicting these coding scores as a function of age group, and we get our estimates for the older adults. We get our estimates for the younger adults. You can see that there are residuals in each case, because even though we estimated a low value of about 45 for the older adults, some people were above that, some people were below that. Although we estimated a higher value of about 62 for the younger adults, some people were above that, some people were below that. So this gives us a sense of how the residuals look relative to the predicted values or the fitted values from our model. The next plot that we'll get is the quantal-quantal normal plot, where again we're looking at the empirical distribution against the theoretical distribution, assuming a perfectly normal distribution. And this actually looks pretty good. We do have some deviations away where we have a little bit of steepening of our empirical distribution relative to the theoretical distribution, right? So on the low end, we're kind of under the theoretical line, and on the high end, we're slightly over the theoretical line. But most of our data points actually fall on or very close to that line. So this actually looks like a pretty good distribution of residuals, and we'd be comfortable saying that this looks approximately normal. Next, we can look at the scale location plot, which shows us the square root of the absolute value of the residuals. So we're taking those residuals, which were positive and negative before, we're making them all positive, and then we're taking their square root. And what we want to look for is, are there any major differences in the scale of the y-axis across the x-axis, right? So again, this is only two groups, so we have kind of two stacks of data. But we have the predicted value for all of our older adults down here, and you can see that here are their residuals. They go from about 0, up to a little over 1.5. For our younger adults, they had a higher predicted value up here. They all had the same predicted value, but you can see our residuals go from a little over 0 to about 1.5. And if we actually fit sort of a regression slope between those two distributions, it looks relatively flat. So it doesn't really look like we have massively larger variability in the older adults than we do in the younger adults. It is slightly larger in the older adults than in the younger adults, but they're pretty much within the same range of each other, and there's no real slope to this line through those two distributions of residuals. So this looks like a fairly homoscedastic or equal distribution of residuals. The final one that we can look at is actually the residuals versus leverage plot. In this case, because we only have two factors, or two levels of our factor, we're actually going to have the exact same leverage value, because as you recall, leverage is the distance on x away from the average x. So in this case, you're either only an older adult or you're a younger adult, and the average is right in between. So everyone has exactly the same leverage value. So we just then look at the standardized residuals as a function of group, and no one in this data set actually falls out as a significantly influential data point. This plot will actually draw for you sort of Cook's distance boundaries of 0.5 and 1. In this plot, we don't actually see those boundaries because all of the data are within the 0.5 threshold, so none of them are major outliers or massively influential data points. So next, let's consider a situation in which we have clear violations. So in this example, we're going to be looking at a binomial outcome. Did a person fall or not during their hospital stay as a function of their score on a cognitive assessment? Now, clearly, hopefully this feels wrong to you to do, right, because this is not a continuous outcome measure like we've talked about throughout the rest of the course, and it definitely is going to violate the assumptions of our statistical tests. So we would never do this, right, but it is useful to show this because then you can see how these binomial data lead to violations of our assumptions, and then we can talk about what we should have done instead when our assumptions are so massively violated. So first, let's look at our quantal-quantal normal plot here. So again, here is our data. We can see, did a person fall or not? We're estimating a model where you're getting either a 1 or a 0 out here as a function of your cognitive score across the x-axis. Here's our line of best fit, right? And what you can see is that our quantal normal plot looks real bad. We have a lot of values down at the lower end, which actually seem to line up with the normal distribution. But then as we get up into the higher end, we have this real sharp, steep slope that comes up to these high values up here, and we have massive departures away from normality. So this is a pretty substantial violation, but we could say pretty comfortably that this does not look normal, right? This is a very different looking plot than what we saw in the previous example, and when we have normality this significantly violated, that's a good indication that we probably actually have the wrong statistical model for what we're trying to measure, and we need to change our approach and attempt a different statistical model. Similarly, in terms of our scale location plot, it's a little bit harder to see here, but again, we're looking at the scaled residuals as a function of the fitted values. So we're looking at what did our model predict for you across the x-axis, and then how far off was it for you on the y-axis. And although most of the data points are down here, right, the vast majority of people did not actually experience a fall in the hospital, you can see that for the slope of all the data points, it actually increases as we're going from left to right. So we're getting sort of a funnel shape where our data are wider over here on the left than they are over here on the right. And that sort of funnel cloud shape suggests that we have heterogeneity. We have a larger error variance over here, and we have a smaller error variance over here. It's a little tricky to see in this situation just because we have so massively more data points down here, which correspond to the people who did not fall, but we still get this funnel shape in our scale location plot, which suggests we have a non-constant error variance. So what do we do in these situations? Well, generally, when our assumptions are substantially violated, that means we've chosen a poor statistical model to explain our data. And this is going to require that we expand our toolkit a little bit and we learn how to use other generalized linear models, of which there are several families. For instance, with this binomial outcome that we have, we could use a logistic regression. If we had count data, we could use a Poisson regression, right? If we had categorical data, we could use a multinomial logistic regression. And if we have ordinal data, we could use an ordered logistic regression. And those are all sort of unique tests with slightly different assumptions and some complicated math that goes into their calculations. But fortunately, everything we have learned in this course carries over to these other sort of modeling approaches. There's a bit of extra information that we have to learn and a few extra steps that we have to take, but coming out of this course where we've dealt with continuous outcome data, you should be well suited to tackle these advanced topics when you have other sorts of outcomes that you need to model. But again, when our outcomes are violated this substantially, that's usually a sign that we actually need to change our approach. There's not going to be a transformation that helps us here. There's not going to be a more complicated model that helps us here. We really need to adopt a different type of statistical analysis, one that is appropriate to the type of outcome that we're working with. Okay, but let's consider a slightly in-between situation where we just have some difficult residuals. We have relatively continuous data, right? But it's going to violate some of our assumptions, or we're going to have some influential data points that we need to check. So here's some data actually roughly approximated from the Utah Asthma Burden Report in 2018, where we're looking at the incident rate of asthma per 10,000 people as a function of different age ranges. So the upper limit of each range is shown, but you can see that we have the different slopes for both men and women within this sample. And you can see we have some nonlinearities here. So for men in particular, there's a large increase in childhood and into adolescence that then starts to level off, and the rate actually comes back down as we get older. And for women, there is also a bump in that early phase. So there's a rapid acceleration out of that first age range into the second age range. But then it somewhat levels off, and there's actually a slight increase over time as women go from childhood into adolescence, into adulthood, and into older adulthood. So the curves, or the distribution of these data points is very different. And if we just fit a linear model to them, which is shown by the dashed lines here, you can see that we estimate a negative going line for men on average, but we estimate a positive going line for women on average. And indeed, if you do a statistical test here, you're going to get a statistically significant interaction. But first, let's look at the residuals that we get. So again, if we are estimating these lines and we look at the difference between each data point and these lines, we're going to get a distribution of residuals that looks something like this. So it looks pretty good, kind of in the center of this distribution. But then we have these tails that look non-normal. It looks like we have thicker tails in our distribution here. And that's, again, is important that we're looking at the distribution of residuals, not at the distribution of the data itself. Because although those two things can be related, our model assumptions depend on the distribution of the residuals, not on the distribution of the data. So to start with, let's look at the quantal normal plot for this model, right? So again, we are estimating a model where we have an effective age, we have an effective gender, and we have an age by gender interaction. So we're estimating these different slopes for men and women, and then we're looking at the difference between each data point and those slopes. We convert those residuals into standardized residuals, and we see how they fit against a normal curve. And you can see that we start to get pretty big departures from normality pretty fast. So at both extreme ends of the graph, we have a lot of lines that are pretty far, we have a lot of data points that are pretty far away from this line. So this is a much larger violation of normality than we saw in the first example. So we're getting a much less normal distribution of residuals here, and that suggests that we might want to adopt some sort of transformation or some other statistical approach in order to deal with our data. We can also look at our scale location plot to get a sense of the homogeneity of the variance. And you could see that at the low range, right, when we're predicting relatively low values in terms of asthma rate, we have lower residuals, right? So they're around 1 or less until we get up into the 20s. We have a greater density of points up here, but we also have a greater variability. And especially as we get up toward high levels of asthma rate, we have much larger residuals, or absolute squared residuals here. So we get this sort of J curve here, where we have relatively constant variance throughout this part of the graph that then accelerates upward, and we get a much larger variance at the high end. So this looks like we also have a pretty substantial violation of heterogeneity, or the homogeneity of our residuals. So what do we do in this situation? Well, in this situation, right, our violations weren't nearly as bad as they were when we had that binomial outcome. So we might not necessarily have to completely change our approach, but we might want to transform the outcome variable before running this analysis. And we could use either like a square root transform, which is useful in dealing with count data, or we could use the log transformation, which is more useful for extreme positive skew. But we could either square root transform or log transform the data first, and then rerun a similar model. Visually assessing our data, though, we might also be able to resolve this problem by considering different models. So in this example, we have a nonlinear relationship between age and rate, but specifically at low values of age. So we could adopt alternative modeling approaches to either use a spline, use a higher order polynomial, for instance, quadratic or cubic effects of age, or we could even treat age as a more categorical predictor, and that might provide a better explanation of our data and lead to better behaved residuals. So we don't necessarily want to, transform our outcome in order to shoehorn it into an inferior model. We might actually want to try testing different models that allow for a little more complexity and can actually handle that nonlinear relationship, right? Transformation somewhat assumes that our model is correct. It's just a little fiddly thing in the data we need to fix. Looking at the data, though, we might actually want a more complicated model and see if that will solve the problem within our residuals. So that's something to consider as you look at these different situations, is that there's not necessarily going to be a one-size-fits-all solution. And sometimes it might involve doing something to your data, other times it might involve doing something to your model. But as always, right, the error is the difference between the model and the data, so you can try to implement a fix in either of those situations to actually get better behaved residuals.